Okay, so in this video clip, we're going to run through here in this Google Colab using R code predominantly and some Python code. We're going to estimate the value of bonds, the value of the duration. We're going to estimate yield to maturity. We'll demonstrate that with some code. We're going to get some code from the Derivmkts R package. Set it up here as a set of functions in this Colab, and then using the BERT XL add-in set out user-defined functions that make use of bond pricing functions for bond pricing, internal rate of return, duration, convexity. Okay, so to get the ball rolling then, first things first, because we're going to use R in this workbook, we'll load in the magic R cell. And basically we're connecting up to the server here, but in addition, we're also going to make available R and in this Colab. We just need to, in front of whatever code snippet we write, include in this double percentage sign and then R. Okay, so very simply, we start off with a very simple bond example. We have a bond, it's going to pay 6% coupon each year at the end of each year for 3 years, and we should discount at a rate of 5.6. In present value terms, that involves discounting at the 0.56%, year 1, year 2, year 3, and we get a present value of 1,010.77. Now, I've done this on Vinegar Hill. I will leave a link, and I have other video clips explaining the problem, but that's a standard basic bond pricing problem in finance. Of course, we could very easily estimate that in the Colab by just executing the snippet of code. So just numerically use the Colab as a calculator, very straightforward calculator, where I write in the values here of 60 divided by 1.056 plus another 60 corresponding with this term, and then the coupon and the face discounted at the 1.056 to the power of 3. So that's a standard problem, and it's easy to sort. And before we had set that out, I'm going to leave here below the video a link to this Colab. But we could also set it up in Python, set up a loop, identify the cash flows, the time periods, the discount rate, and then execute the code again. So the problem we have here, the 60, 60, and 1,060, that's our cash flow array. Our time periods are going from 1 to 3, so up to 4, but not including 4. The risk-free rate is, the yield to maturity here on the bond instrument is given as 5.6%, and we import in NumPy, and we use the power function then to discount each of the terms, and we get a value of 1,010.77, which corresponds to what we had here in the manual estimation. Okay, so that problem then could be, and if we change a little bit, maybe to, instead of discounting at 6% or 5.6, what if I changed our code not to 5.6 but to 6%? If we were discounting at 6% and the coupon was 6, then the value of the bond would be its face, right? So we can see if we run this calculator, if we go back to discounting at 5.6, we get 1,010.77. But of course, if the discount rate and the coupon rate are the same, then the value of the bond is its face, and the face value was 1,000. Okay, so that's the definition of a par bond. Again, manually, that's what how we would set that up, discount it to 6%, and we get our 1,000, so that corresponds. Now, if we convert this to an annuity type calculation, then instead of discount each of the cash flows individually, we take the coupon, which is a constant, uniform amount of money that arrives at uniform intervals, and if we're discounting at the 6%, we apply this present value annuity formula, and then we discount the redemption value or face value separately, and we get 1,000 again. So no difference there. If we were to run this using the 5.6% annuity and follow this, of course, we get the original figure here, 1,010.77. But if we change each of these to 6% and execute, right, what we obtain here is the 1,000. So if I run this where I'm discounting at 6%, 1,010, but if I discount using the annuity at 5.6, then the value of the instrument is higher than the face. So if the discount rate is lower than the coupon rate, the value of the bond, present value of the bond estimation will exceed the face value of the bond instrument. Okay, now fortunately, some of this we could codify. A nice function here that we're going to use is a function developed in the Derivmkts R package. I'm going to go in here into the GitHub. It's Robert MacDonald and his celebrated textbook. And he set up a series of different financial estimations here, but what we're principally interested in this instance is the bond, and the formula here, or the functions that he's defined for pricing the bond instrument, and the duration, the convexity, and the yield to maturity. I'm going to introduce these here into this Colab, and I'm going to run the bond PV function, and then note that the way the function works is it's the coupon, which we had before as being 60, and the maturity is 3 years on the instrument, if you recall, 3 years, and we're going to discount at 5.6, so that was the original 5.6. And the face is 1,000, and we should get 1,010.77, right? Following from where we had been before. Let's run that and see what happens. We get 1,010.77. Okay, now if we change that, if the compounding is twice a year, change that to 2, then the estimation would change. So we have the coupon, but it occurs twice a year. So now we have this type of estimation, and by changing the frequency from annual to semi-annual, now we get payments of half of 60, but twice a year. And if we run that, we get 1,010.90. So it's a little bit higher, 91. Okay, if I change back to 1, it's the original estimation. If the frequency is twice a year, the value of the instrument would increase by a bit. Using an annuity structure, we make that adjustment. Again, if we run our estimation, if we use this bond PV 60, coupon, maturity, discounting at 5.6%, face value of the bond is 1,000, and frequency of the coupon is twice a year, so semi-annual coupon, value of the bond is 1,010.91, right? Rounds to 91. Okay, so we typically, when we're looking at bond pricing, we're interested in not just the price of the bond, but the duration, the yield of the instrument, convexity, right? So the duration and convexity basically give us a sense of the bond price sensitivity to change in interest rates, right? That could be important if you were a large fixed income portfolio manager. You would be interested to ensure that the duration of your assets were linked to the duration of the liabilities, and you would like to know the nature of that relationship, right? You would like to know the to what degree, if your assets adjust, your liabilities adjusts in stepwise. Okay, so if we run all of these functions, again, this is coming in from the GitHub, or you could go on to RDRR. The source code for these functions is available there as well. You can take a look at that. But we've executed this code, and so now we have 4 functions which we should be able to use below. So for instance, going back to the question we had, if we were to run estimate the value of the bond with these particular parameter inputs, we would get 1,010.77. And if we turn the question on its head and said, okay, we know the value of the bond instrument is trading the market for 1,010.77. It's a 3-year instrument. But what rate of interest or yield to maturity would ensure that this entity, this flow of discounted sum of discounted cash flows would equate to 2,010.77? We would typically have to do a grid search, which we do here. So if we run our snippet of code here, we get 2 outputs. One is in the first instance, we say, okay, we know the coupon is 60, the maturity 3 years, the yield is 5.6, the principal 1,000, and the frequency is once a year. Frequency is once a year. We should get a value then here of 1,010.77. But we could ask the question the other way: what if we know the value of the bond instrument is 1,010.77, right? Then what is the yield to maturity? And in that case, we know it should be 5.6. Now, if I said that the price of the bond was equal to 1,000, instead of the 1,010.77, then the yield to maturity, knowing that it's a par bond, the face is equal to the price, the present value of the bond. If we include here the price, which is the market value of the bond instrument, if it was trading for 1,000, then what should the yield to maturity be? Well, in that instance, it's a par bond. And like what we saw before, the only interest rate here that would produce a present value equal to its face of 1,000 is 6. So if we run that estimation again and estimate using the function we had set up from a Derivmkts package, then the value we should obtain is not 5.6, but 6% exactly. So let's run that and see what we get. And we get exactly 6% for the bond yield. So we have the bond yield and we have the price. And we have both of those, we bind together and report out. Now, if I change back price is equal to the price, or we could say 1,010.77 and run that again, then we should revert back to 5.6, which is basically what we have. And because it's not, it's a little bit out, it's probably better to write price here so we don't get that scientific notation. So now it's quite exact. Okay, so okay, that's our Derivmkts functions, but we would like to explore duration, convexity, and perhaps we could set up our estimation in a spreadsheet. To understand duration for a moment, duration is a measure of the sensitivity of the bond price to change in interest rates. It's commonly used in fixed income as a measure of risk for the portfolio manager. And if we were to do a manual estimation of duration, typically we're estimating the, if we took the bond, for instance, here we've 1,000, a bond with a face of 1,000, coupon rate of 10%, risk-free rate of 10, T is 5, M is equal to, so the frequency of the compounding is twice a year, then the present value of the bond would be its face, which is 1,000, right? And if I set up the duration estimate, if I estimate the duration by discounting each of the cash flows, so taking each of the coupons for the period of it's 6 months, so we have 2 by 5 years, that's 10 payments of not 100, so coupon rate is 10%, 10% of 1,000 is 100, half of 100 is 50, so we're going to get a series of not 5 but actually 10 cash flows because it's semi-annual over a 5-year period, and instead of getting 100, we're getting 50 every 6 months and the face value at the end. And then to estimate the duration, we discount the coupon and we multiply it by its respective time period. And so we get the face value of the bond instrument. And then when we take the present value of the cash flows multiplied by the respective time period, sum up and divide by the bond price, that's what produces the duration. Right. So in effect, to estimate the duration, normally we would have to go through this series of estimations. It's a bit involved. Fortunately, we have the duration function here, and we can go below to see if we can reproduce the estimates that are provided here. So if we take the data as given, look, it's the coupon rate is 10%, the maturity is 5 years, the frequency is twice a year, the principal is equal to 100, and the yield is equal to 10%. Then the coupon is equal to the coupon rate multiplied by the principal. And so that's the annual coupon. And then to get the duration measure here, we simply use our function duration, and it's not the modified duration, it's which involves, for the modified duration, we typically take the Macaulay or normal duration and divide by 1 plus the yield to maturity times the frequency of the coupon payment. Okay, so to get the Macaulay duration, right, we follow this series of steps, and we can work that out here in using our R commands. Okay, now let's do this in RStudio. Let's take the functions that we have here, right, and copy. So we can say copy cell or copy selection fine. Let's go into RStudio for a moment. And what we plan to do is to RStudio is to set these functions up in RStudio, run the estimation, and then transfer the functions into Excel to create user-defined functions and then verify our results. So I'm going to go File, New File, RScript, Control V. So now we have those functions for the bond price, the bond yield, the duration, and the convexity. I'm going to save the file because I want to set this up in Excel and use the functions here as user-defined functions in Excel. I'm going to save the R script file to the BERT2 folder in my documents, and then enter into the functions, and then we'll say bond pricing deriv markets. Okay, and I'm just leaving that there so I know what it is, and then I'll save. So I'll run the functions, I'll execute the functions. And make sure I save. And then I can come down below and just verify the results that I have obtained here. So I'm going to verify, okay, let's take this estimation again and verify the duration is 4.53 for the 5-year bond. And the bond price is equal to 1,000 because after all, it's a par bond. Semi-annual, 5-year bond, in coupon rate and interest rate the same, so it's a par. Value of the bond would be its face, and then verify the duration. So we take our values here as given: coupon rate 10%, maturity 5 years, frequency equal to 2 years. We'll copy the selection and we'll run then in RStudio, and I think it's this one. Okay, Control V. So we attach then to the object the parameter values, and then we get the price. So we get what we've obtained here is the price of the bond, which is at 100, the yield to maturity, the duration to 4.5, and then the modified duration. So Macaulay duration, the modified duration, and then the convexity. Okay, now let's verify that in Excel. So save that. Okay, I'll bring in my Excel file where I had made the original estimation. And now I'm going to go into R. So let's use the R commands that we had saved. And let's verify the results. So basically we have equal to R dot, and then we had a function for bond price or bond PV, and the coupon was equal to, if you recall, 50. So it was equal to 1,000 multiplied by 10% divided by 2. That would be 50. Then the maturity is equal to 5 years. The yield is equal to the discount rate. The principal is equal to the face value. The frequency was twice a year. And so the maturity is equal to 5, the yield is equal to 10, the principal is equal to 1,000, and the frequency is twice a year. Okay, so remember it was supposed to be the annual coupon. I didn't have to divide by the frequency, so it's the annual coupon. We put in our formula and we get 1,000, which is the same as the result here. So both results using whether we use manually discount the cash flows, right, or estimate using the function, we get the same result. Now, final thing we can do here, we want to get the duration. So R dot, I think it's D duration, and again FX, and the price is 1,000. The price of the bond is 1,000. Let's okay, 1,000. coupon is equal to 10%. The maturity is 3 years, 5 years. The principal is 1,000 and it's twice a year. So twice a year. And is it modified? False. And of course, it's not the coupon rate, it's the coupon. So it's basically, it's the face value multiplied by the coupon rate, which is, we're going to use here 100, and it's not modified duration. It's false. Okay, and you can see we get the same result. Okay, so we can see here that the duration we're getting from our duration is tallying with the result we had got obtained in the spreadsheet by performing the estimation manually. And I'll leave a link to the video clip outlining that manual estimation. So function in that respect is looking good. We can also get the modified duration. So again, we could perform the same estimation before. So if we take these sets of results and copy and paste, Control V, equal, and we want to get modified duration, we just change to true, right? True. And return, and we get that 3.860. So that's the same. That basically is with modified duration, you're taking the duration estimate and then you're adjusting and you're dividing by 1 plus the rate of interest divided by the frequency of the coupon payment. Okay, now there's a very interesting or a very nicely presented bond price question in the, I have the link here, the PDF. So this is the California Debt and Investment Advisory Commission. And there's a number of estimations worked out there and an explanation of duration and Macaulay duration and modified duration. No estimate for convexity. Okay, we can verify the results obtained there. So the estimates, if you like, using the numbers presented here, can we replicate the results using the Derivmkts result? I've done this on a spreadsheet previously, but if we take the functions as presented in the Derivmkts package for simple bond pricing, if we take the coupon rate as 10%, the maturity equal to 3 years, the frequency of compounding as once a year. So basically we discount 100 at 7% each year for the 3 years plus the face value of 1,000. The yield here is 7%. So less than the yield to maturity, 7%, so less than the coupon. And if we execute our code here, you can see the results obtained in the CDIAC publication explaining duration and Macaulay duration tallies with the Derivmkts R package. So the 1,078.72 is the same, and then the estimate for duration, the Macaulay duration 2.7457. It's the same. Okay, 5.8 rounding goes to up to 5.8. Okay, so same results And we also, the valuation here, if we look at it, if it is 7%, if we change the price to the face value, we should get 10% for the yield to maturity. That would be par bond, but the reality is, in this instance, we're going to go with the price is equal to the price, which was, we found to be 1,078.73. In that instance, the yield to maturity would be 7 as expected. So that's demonstrating that the yield to maturity estimation works, the duration works, modified duration, find convexity. We can check at a separate date, but the convexity estimation is there as well. Okay, I'm going to leave that explanation there.